This video is going to give a conceptual understanding and an introduction to Gauss's law. So we're going to begin by introducing Gauss's law in the equation form. Then we're going to talk about how we're going to apply that equation to various physical situations. And then we're going to talk about symmetries of Gauss's law. So to begin by talking about an introduction to Gauss's law in the equation form, here is Gauss's law. It says the integral over a closed surface of E vector dot ds is equal to the charge contained or inside that closed surface divided by epsilon naught, the permittivity of free space. So to go through really quickly here, the weird looking double integral that we have with a circle means the integral over the closed surface. So if you have some form that you're trying to enclose a surface with, this means that you need to entirely enclose it. We'll see what that means in a moment. E vector is the electric field. ds is some tiny surface element. Qin is the charge contained within the closed surface. And epsilon naught is the permittivity of free space. So let's see how we can use Gauss's law in practice. And so this is going to be a short application of it. So consider some positive charge plus Q. We know that it radiates electric field lines away from it spherically. And what we want to do is we want to apply Gauss's law by using various closed surfaces. So the first one that we're going to consider is putting this charge at the center of a cube. Now, it turns out that if we wanted to do calculations with Gauss's law, this would actually be rather difficult because there is an angle in between the dA vector, or the surface vector that is perpendicular to the surface, and the electric field vector. So when we're evaluating the dot product, the integral of E dot ds is the important thing to consider here. E dot ds is going to be the magnitude of E times the magnitude of ds times the cosine of the angle between E and ds, or in this case, dA, because it's a flat surface. Now, the problem arises in doing the calculation here in that the cosine of theta, this angle, is going to be different for every single point on the surface. And you can imagine that you're looking at the point at the center of the surface, the electric field and dA are going to be in the same direction, and at all other points on the surface, you're going to have a different angle in between E vector and dA. So really, trying to enclose something with a cube, if something's spherically symmetric, is not the best way to go about it. But what we can do is we can try to enclose this with a sphere, because this exhibits good symmetry for the charge that we have. And here we see that ds vector is going to be in the same direction as E vector, which means that for every point on the surface, the angle in between ds vector and E vector is going to be 0, meaning we can evaluate the cosine of theta as cosine of 0, which is 1. And this is a really nice thing for us to have because it allows us to reduce this from the integral of E vector dot ds vector to just the integral of E times ds. But we can go a step further here by saying that the electric field has the same value at every point on the surface. And so this integral of E times ds can become E times the integral of ds. Now, whenever we have an integral of some infinitesimal, and it's only the integral of the infinitesimal, that's just going to form the large piece, right? So we have some tiny little surface elements, ds. The integral over these means that we're adding all of those ds's up to make a larger surface. And so we can say then that this is going to be E times s. Now, because we're dealing with spherical symmetry, s is going to be the surface area of the sphere. And so that's going to be 4 pi r squared, where r is the radius of our Gaussian surface. Now, we've evaluated the left-hand side of Gauss's law. We can evaluate the right-hand side by considering what the charge is inside this sphere. And in this case, this is just going to be plus Q. Now, we can solve for E here by moving the 4 pi r squared to the other side of the equation. This says that E is going to be equal to plus Q divided by 4 pi r squared times epsilon naught. And we can recover our unit vector r hat because we said originally that the electric field is pointing radially outward. This says that E vector is equal to 1 over 4 pi epsilon naught times Q divided by r squared times r hat. And this is a really interesting feature of Gauss's law and an important feature in physics when we're looking at a new theory or a new way to describe the physics. And that's that it recovers the results from older theories. So here we're finding that the electric field from a point charge is the same as we found when we were applying Coulomb's law previously. And we came to this conclusion purely through geometrical arguments. And it's very important that when we're bringing in a new way to look at things, we recover the same old results. Okay, so now let's look at some more symmetries of Gauss's law. We've already talked about the spherical symmetry, so we'll talk about that really quickly here. So in spherical symmetry, we have some sphere, has some radius of r, some tiny little surface element ds is going to be pointing perpendicular to the surface. And so when we add up all of those tiny little ds's, we're going to find the surface area of a sphere is just going to be 4 pi r squared. We can also look at cylindrical symmetry. And when we're looking at cylindrical symmetry, we have a cylinder that has some radius of r. It also has a length of lowercase l. And we can look at the surface element that are around the curved portions of the cylinder. And these tiny little ds's, when added together, are going to give us a total surface area of the outside of the cylinder, which is going to be 2 pi r times l. Now, a small thing to take into consideration here when we're talking about the integral of the closed surface, we need to include the flux through all sides of the Gaussian surface that we're drawing around the charge of interest. And in the case of cylindrical symmetry, a lot of times we make an approximation to say that if we have an infinitely long charge distribution, the flux out of the two end caps, the circular portions, are going to be 0 because the electric field is going to be perpendicular to the ds vector. Okay, so that's it for our introduction to Gauss's law. The next video is going to talk about insulators and conductors. Hope you enjoyed this video. Thanks.